Okay, welcome guys to the second session of learning about voltage. In the first session, I wanted to basically cover what it is, how it's measured, what it's measured in, and so on. What you guys will probably notice is that we didn't cover so much of the assessment questions in the first session, because to be able to answer your assessment, you need to know what it is you're talking about. All right, so the first session was designed to cover the what. This session now is going to be more dedicated to getting the assessment questions done, together with obviously learning about the other bits that we need to cover. All right, once again, you should be able to see my shared screen. Okay, once again, it's the PowerPoint. I'm going to stick the annotations up there, and I'm going to get started. All right, so excuse me, measuring voltage is definitely the more common test you're going to be doing. All right, before you go to work on anything, you've got to make sure that it's dead. All right, you've got to make sure that the supply is off. Measuring current, which we've covered in our first session, is something which me personally very, very rarely you would do on site. Maybe in my industrial work, I would measure it with a clamp meter, but definitely I can't think of an occasion on site where I'd ever measure current in series with a multimeter. But on the other hand, the voltage test is the most common. All right, every single time I think I've ever been to a job, I've done a voltage test, because if I got to work on something, you've got to be sure that it's off. All right. Same thing as well, if you're fault finding, you want to know if the voltage is there or not. Switching back on, if I switch something on and it doesn't come on, you can't assume that the device is faulty. You've got to check to see if there's voltage there first. That's always your first step. See if there's voltage there, and then move on from there. All right, later on in the course, guys, we're going to be talking about measuring resistance. That's another test which is super important for fault finding. But for safety, voltage is going to be the one that you guys need to know inside out, back to front. Okay. We talked about last week that voltage is the potential difference from one place to the other, the difference in charge, if you like, or difference in electrons from one place to the other. And then we measure in parallel. All right. I'll skip this page, and this is the symbol and the tester that we talked about last time. And then we've got an example here. Okay. We've got the picture on the left-hand side shows that the red cable from the tester is going to the positive side of the light bulb. The black is going to the negative side, and that you've got a 12-volt battery feed in this, and then the voltage is 12 volts across there. All right. So once again, we said last week that the battery is providing the pressure, the circuit is closed, it's working, and the light bulb is using the pressure. All right. So obviously, if I was to compare this side to this side, we've got 12 volts difference. Okay. All right. So when we're testing, all right, guys, a tester is something which is always outside of a circuit, or we don't want the circuit to know we're testing it. Okay. So like we said when we were talking about measuring current, current has to flow through an ammeter. All right. Now, for the circuit not to notice the ammeters there, the ammeter must have an extremely low resistance, so the current can flow through it without noticing. Okay. The opposite is true for when we're measuring current. Okay. So I'm just going to draw on our picture here. I'll draw it on this one. Oh, that's too wide. Bear with me. I'll draw a red cable in. So that's my positive in the circuit. And then there's my positive cable there. Changing the color to black. The bottom one is already black, so I'll just change my meter there. Okay. All right. So let's look at some values. Okay, so let's put in this side 12 volts. What do we have? So we don't have any other values. We don't have a resistor or current or anything like that. And I don't care about that at the moment. What we care about is that we talked about an ammeter having a low resistance. let's say an ammeter resistance is, let's say 0.01 ohms. All right, that's a nice low resistance that current is going to flow straight through. No questions asked. Easy. Okay. So everyone in the room should have pretty good with. You're probably sick of it by now. The triangle. Okay, it's a really important one to remember every time we do stuff like this. Is the Ohm's law. So we would have done that in our first session. B. And then we have I by R. Okay. So remembering how to use that and that you cover one to work out the other two. All right, if we have that there, let's put in some values to help us understand what's going to happen here, okay? So I'm going to make this like 12 ohms. Okay. There's a 12 ohm light bulb there. Making this nice and easy for me, all right? Don't want to think too much about it. It's too small. There's my arrow to show my current flow. And to work out the current flow there, I'm going to be I equals V divided by R. Once again, guys, all right? If you're not sure where I got that from, look at our first sessions. If I want to work out I cover it, and it leaves me with V over R like that, okay? Excuse me. All right, so V over R, so nice and easy. 12 over 12 leaves me with 1 amp or 1A of current flowing. So I'll write that in there too. 1. All right, so this healthy circuit that we've got going on over here, we've got some values in now. And we can see what's happening there. All right, so remembering this maths, okay? This voltmeter now, remember we go in parallel. So the red goes to red, the black goes to black, okay? So let's say that we've got this on the wrong setting. We've accidentally put it on, see if I can seamlessly do this. That's wrong. Bear with me. All right, just try and cover that in blue for a second. And let's say I've put it on the ammeter by accident. Okay, so I've got an ammeter across the supply now. Well, as you can see by the top, my ammeter resistance is extremely low. All right. So what does that mean for us? What it means for us is that the current is going to, let's draw the current in orange. Why not? So the current is going to leave there. It's going to come across there. So again, if we get to the word junction, all right, it's going to get to this point here where, let's say my tester is, okay? It's got two options. It can go that way, or it can go that way, all right? Now then, current is a little bit like the person teaching you. It's lazy, all right? It's going to pick the easiest route. Okay, so my lamp has 12 ohms. Ammeter, which I've accidentally connected, has 0.01 ohms. Okay, so what's going to happen here? So again, I need my I equals V over R. Right. So the supply is still, oops, excuse me, still 12. But my resistance now has changed to 0.01. Just to make sure I don't make the mistake, it's 12 divided by 0.01, which gives me a new value of current of 1200 amps. All right, that's the problem. If we were to connect our current, is there's nothing in the way of it now. All right, so let me just get my eraser to get these off, and I'll do the same orange color to show current, but this time I'm going to draw it as this. So you don't not tell me, but you look to see where there's anything standing in the way of this current flow. Starts here, through the conductor, through the switch, through the conductor, through now the lead, which is a cable, it's a conductor, through the ammeter, which is 0.01 ohms, so that's a conductor, through the black lead, which is a conductor, through the negative, which is a conductor, back to the battery. Nothing to stop it, nothing to slow it down, and that's where this huge number comes from, all right? And that's only from 12 volts, all right? So current, guys, is heat, same thing in DC circuits. So that's gonna create a lot of heat, and there's a serious danger there of, because you've connected that in, best case scenario, you've got to buy a new tester, all right? Worst case scenario is the tester could be damaged, it could have damaged and blown up in your face, could have burnt you, who knows, all right? So something as simple as choosing the wrong setting on a multimeter can cause serious issues like that, okay? All right, so what does that mean for us? So what we want is a voltmeter as a very high. I'm going to leave it in orange. I can't bother to change it. All right. To I'm going to say limit current flow, because if I put a number against it, even if I put 20 mega, which means 20 million ohms, that still works out to be some amount of current. A very, very small amount, granted, but still, it's still going to be an amount of current, okay? And where that's important is, just to make the numbers a bit easier, I'm just going to put 1 mega ohm as my resistance of my voltmeter, okay? So if I look at how much current is going to flow through my voltmeter, then once again, let me change the color. Don't like that color. Let me change it to I equals V divided by R. Right? Okay, so V is 12. This time R is 1 million without the spaces. All right, which 12 divided by 1 is a very, very, very small number. Okay, which very small, okay? Which this is a good thing, all right? Because the tester has such a huge resistance, very, very, very small amount of current is going to go through, okay? Okay, so why are we talking about that? It's because when we're testing, we've got to make sure that we're testing voltage, we've got it on the right setting, all right? But there is something which we call voltmeter loading, and that is one of your assessment questions, all right? So let's say, I'm going to have to draw it white. Give me some room there. Okay, so let's say we have in our circuit here, at that point, fill that back in. Okay, so let's say I want to measure current and voltage at the same time. Okay, so we worked out earlier that this 12 ohm lamp drew 1 amp of current. Okay, so we already had that. All right. So in a healthy circuit, this is going to show 1 amp. All right. So when the circuit is running normally, 12 ohm light bulb, 12 volt supply, I is V over R, will give us 1 amp. Okay. All right. Now look, when I connect my voltmeter in, it's like I'm connecting another load. All right, because my red goes to red, black goes to black. It's like I'm plugging in something else to the circuit. That's what voltmeter loading means, okay? It means that when you put the voltmeter into the circuit, regardless of how good it is, they always draw some amount of current. Now look, we've worked out how much ours is gonna draw. It's a tiny amount, all right? But it still changes the actual value the ammeter is gonna read to 1.000012. Hopefully, guys, you can see where I got that number from, right? If I draw my double arrow back to back, you can see that those two there are linked. So it was our normal current was 1 amp. Voltmeter current taken is 0. Voltmeter, when we connected it, we worked out I is V over R, 1 million. So 12 divided by 1 million, it was that number there. That's how much current the voltmeter takes. So it's hardly anything. We're not going to notice, but this is what voltmeter loading means, okay? So there's the current taken by the voltmeter. So to work out the total current, the ammeter, will read when we are testing for voltage. At the bottom, we can say that it's the normal current plus, if I can move that across, that'll be great. Normal current plus the voltmeter current. All right. Apologies for not being able to add that on one line. That is bugging me. All right. So the normal current plus the voltmeter current, which is normal current was 1 amp. And then we plus our 0.123412 amps, which leaves us with a new value in the ammeter reading of 1.000012 amps there. All right, you will notice that if I circle it in red, new reading, which the ammeter shows, the way we worked it out, is the same one I drew up here that the ammeter was reading. They are the same thing, okay? That's what it reads, that's why it reads it, all right? So the voltmeter will take a little tiny bit of current. It's what we call negligible, all right? So we don't actually care that it takes that much because it's not gonna make any difference, all right? That's a good voltmeter. So it's gonna read very close to what it should read, okay? That's not gonna make a difference, which is gonna be noticeable when we're working, all right? That's it's fairly technical, all right, for what is only one of our early sessions, all right? Hopefully the notes there and comparing places on the diagram is showing you that, okay? That should pretty be straightforward in the sense that, guys, when we test for voltage, the circuit is going to slightly increase in current. You wouldn't notice unless you've got an ammeter reading that. Obviously, as soon as I then remove my voltmeter, my current will then go back to 1 amp, which it was when it was correct. All right, beautiful. So that should help us with why the voltmeter has a high resistance, to stop current flowing through it, or to limit, all right? To limit current flow, to make sure it's as small as possible. The more expensive the voltmeter, guys, the higher the what we call internal resistance, or the resistance inside of the voltmeter. All right, so you're paying for that because they're more accurate. All right. So there's why does a voltmeter have a high resistance, and what is voltmeter loading? Hopefully that makes sense. All right, beautiful. On the screen in front of me, we have what's called an example of a volt stick. Okay, so a volt stick works by, this particular type works by, they call them proximity. Let's say that's correctly spelled. Testers. All right. Proximity means close to. So it works by detecting an electric field. That's what the voltage produces, an electric field. Particular field when close by. All right. So if you've got one in your hand and it's off, obviously there's no electric field by you. If you hold it up to a power point or a light switch, then it should illuminate on the end there. All right. There's lots of different types of these things, guys. When we're testing, whether this be voltage with a multimeter, whether this be voltage with a volt stick, there is a test process that you must go through. And I'm writing it up here in capitals. This will be something that follows you around your life, if you, your electrician life, and in all of your practical exams. Remember this saying, get it tattooed on your head if you want to, all right? Because if you do, then you won't have an accident. Okay, prove, test, prove. What does that mean? So this is the process. One of the questions, guys, that in the assessment talks about, what is the correct process for using a volt stick? All right, there's nothing more dangerous than getting a volt stick out of your pocket, holding it up against a cable, it not light up, and then saying, great, getting your brand new insulated $80 cutters out and cutting through a live cable and putting a nice big hole in it. All right. So why didn't it light up? Well, if it's been in your pocket and the batteries have run flat, it's not going to light up. All right. If you've held it against some of them, especially with flexible cable, the cable is turning inside. It's not straight through. So you might hold it up against an earth or a neutral, and depending on the tester, they may not light up. There's lots of different things, all right, but most of the time it's because the batteries are flat, okay? And people think that it's safe because they haven't followed this process. You're gonna have accidents then, all right? Prove, test, prove. So step one, first prove is to prove the tester on a proving unit. Now, the proving unit is something you can purchase, which it gives you a known voltage. So the 230 volts is a special battery pack, all right, which simulates live testing. If you do not have access to a proven unit, you can prove on a known supply. All right, so let's say you're working on a lighting circuit and you're isolating the lighting circuit, and you know, for example, the fridge is in the kitchen circuit and you're not working anywhere near that, then if you want to use something on that circuit, then that's okay. All right. So you prove the tester to make sure it's working. All right, so I get it out of my pocket. It may have been in there 6 months and I haven't done any work. I go up to a socket in the kitchen and hold it against the socket and it lights up. Right, okay. So I've done my isolation and I hold it against the cable, for example, that I want to cut. All right, so that's the test. That's the test, oops, excuse me. That's the test part, all right? So you test the cable or circuit or whatever you want to call it to work on to full voltage to see, voltage to see if there's any voltage there. All right. Let's say there's nothing there. If obviously, guys, if it lights up, then you've isolated the wrong circuit. I'm just going to add in there, isolate circuit. Apologies if that's caused a bit of mess on your notes. Okay, so isolate circuit and test the cable circuit to work off of voltage. Obviously, if it lights up, you've isolated the wrong one. We're going to assume that it didn't light up, all right? Now then, the reason it's proof, test, prove is because if you prove an unknown supply, it lights up, and then you hold it against the cable to work on it, it doesn't light up, there could be a worst case scenario of your batteries were good for one test and that was it, now they're dead, all right? They've given you the false sense of security that you've created, you've switched the supply off, which is why you have to always reprove the tester. Prove again, all right? It's reproving on the known supply from step 1. Okay, you have to put the tester on the same thing that you did in this one, and I'll do my little arrows across, up and back. Okay, now if I switch my circuit off, all right, I got my tester, I put it on a known supply or a proving unit, it lights up, I hold it against the cable I want to cut, and it doesn't light up, and then I go back to the first step, so the socket or the proving unit, and it lights up again, then I know that the test is working, and I know that it didn't light up on the circuit I want to work on, which proves the circuit is dead. All right? Only if your test passes the 3 steps can you work on the circuit. This is a little bit far away from you guys when you're Cert 2, all right? A Cert 2 course. Still, when you're doing your electronics, you should be following the same rules because it gives you the sense, a state of mind of always isolating, all right? And doing the right thing. Any of you guys who go to work experience, prove, test, prove. Always remember that, okay? If someone, they shouldn't, but if someone asks you to work on something, make sure that we know it's the voltage that we need to test if they give you a multimeter. Prove, test, prove, all right? That's the correct process of that, okay? All right, okay, so I'm not sure if I mentioned this last week, but we've got some advantages and disadvantages of using certain voltage indicators, all right? Advantages, so what are the advantages of one of these things? Okay, well, they're light, easy to transport, okay. Some of them have got like, can pick up, I'm not going to say high voltage, I'm going to say you can pick up different voltage ranges. The Milwaukee, for example, has a yellow light for 0 to 50 volts, and then greater than 50, all the way up to 1,000. I believe then it has a yellow for that one, and that one is a red LED. All right, so for you guys who are working with single and 3-phase, your 230 and 400 volts, obviously you're going to have a red indication there. All right, another major advantage of that, okay, is that you don't remember that voltage is the difference from one place to the other. All right, now this isn't how this particular tester works. All right, this is picking up the field when it's close by. So you don't have to, I'm going to say, break into or cut the cable to test the circuit. If you're in a roof space and you've got cables everywhere, the last thing you want to do is start chopping them all up, all right, to see which one is the one you want to work on. You want to be able to do that without breaking into the circuit, all right? So this is where these things can be helpful, all right? Obviously, they can be used to detect whether you've got live cables behind a wall, plasterboard wall or something like that as well, all right? I would say that they're far less reliable for that, but I know that the good sensitive ones can do that as well, all right? Detect whether live cables are behind the wall. Okay, so there's your advantages there, all right? Let me move that up to give me a bit of room for my disadvantages. I know in your assessment, guys, there's a few different types. They all pretty much share the same type in and all right. Okay, so they all pretty much share the same advantages and disadvantages. All voltage indicators are going to be like easy transport. They're all designed for you to be able to test without breaking into circuits. All right, but they all have similar disadvantages too. Okay, so disadvantage is that they will this can be really off-putting and confusing and make you lose confidence, all right? If you've got cables that are clipped together and you can't get them apart without taking all the clips off, obviously if you hold your tester against even a live cable when, if you've got a dead cable with a live cable next to it, your voltmeter is going to show you that there's electric field there, okay? It can't distinguish between the dead one and the live one. It just knows there's something there, okay, which is a nightmare, and it can be quite dangerous in that sense. Other disadvantages, all right, it's an obvious one. It doesn't show the actual what voltage am I looking at? I know I said the indicator has a 0 to 50 and 52,000. 52,000, is it a single phase or three phase? I don't know. It's just red, okay? And the problem is that the larger the voltage, I'll write this in, the larger the voltage equals the larger the large electric field. So you will find that if you hold a tester close to a switchboard, it will work before you get anywhere near the switchboard. So you obviously can't test individual circuits in there because all the circuits in there are going to switch it on. Unless you switch them all off, they're not suitable for that. That's what your voltmeter with two leads is for, all right, is to do the difference from one side to the other. All right. I know in the test guides it talks about solenoids and all these other things. Those types of testers, have a quick Google search to see what they do. Voltmeters, again, all right, you've got the disadvantages are all pretty much that they don't give you the voltage value, but they've all got their own way of giving you an indication, all right? So your neons and your series have got the LEDs to warn you that there's voltage there. They don't have batteries. The solenoid, it will move. A solenoid is like a moving barrel. So you'll actually feel and hear the tester if there's voltage there. Again, all right, that's no good. It doesn't tell you how much. It just tells you it's something there, all right? So for your assessment tool, guys, the advantages and disadvantages are quite similar with that, okay? All right, clear all. There's a few other examples there about the plug-in testers, multimeter, all right? We've covered them previously. All right, that takes me on to producing a voltage, all right? So how do we produce voltage? We have to look at 4 ways of doing that for your assessment, okay? Okay, so we can do it by converting other forms of energy from sources such as mechanical, chemical, heat, and light. All right, so the heat and light, we're going to go all four. Mechanical is the one which actually produces most of the electricity we use. For this course, chemical is, and I'll explain why in a second. All right, let's move on. So we've got an energy source, wherever it comes from, turns into electrical energy, and then that electrical energy powers our loads, the things we plug in, whether it be heater, lighter, and so on. Okay. All right, so first example of mechanical to electrical is friction. Okay, friction between two materials. All right. The second one is a mechanical stress applied to a piezoelectric element. They are crystals. Okay, you guys have all used them before, believe it or not. You just don't know you have. And moving a conductor in a magnetic field. That's our generators. Okay, so we're going to cover these three now. Friction. All right, we're not going to spend too much time on this one. How does friction work? Okay, like lightning, or like old mate here with the balloons. All right, if you rub the two together, all right, electrons build up on one side. So there's a difference in electrons from one side to the other. If I wanted to get my voltmeter out to measure the difference electrons from one side to the other, then I would have a voltage there, okay? Now for voltage to be able to travel, so when you get a static shock, for example, the electrons are built up to such a high amount that they can actually jump through the air. That's why you might see a little spark when you get a static shock. So there's a huge amount of electrons that are built up, but there's no constant power. There's no consistent voltage to supply them, so you don't get any harm from that. It just hurts. All right, there's no current in that flowing. Okay, like the picture shown here, that you've got a difference, negative to positive, so that's going to attract, and you've got these two here where they've both got a negative charge, so they're repelling each other. The attract and repel is something really important when we're talking about magnets later on. We'll get to that. But friction, we don't really need to worry about that too much. All right, as long as we understand what it does. Building up a charge from one side to the other is a potential difference, which is the voltage. All right. The crystals. Okay, so this is what they look like inside, very, very small. All right, and basically what happens is when you put a pressure on the crystal, you'll hear a click. And the click is the voltage jumping the gap. All right, so it creates, when you put pressure on one of these crystals, they create a large voltage, and that voltage then is used to light certain things. Where they use, think of it yourselves, guys, wherever you press something and you can hear click, 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 click. Where have you heard that before? Give you a few seconds to think. Okay, so those of you who thought maybe the stove, maybe the barbecue, that's where they're used. Okay, that's an example of where they're used. Gas will be sprayed through this area here as you put pressure on this part here. All right, put pressure between these 2 points. It squeezes the crystal creates the voltage, creates the spark, ignites the gas. All right, so that's how your barbecue and your stove work. All right, moving on. Where do we use them? Okay, so there's another example here. Okay, so in one of these lighters, not the one with the wheel that uses friction to create heat. This one, you put pressure on the crystal, creates a voltage across these two nodes here, and then the gas sprays through that voltage and lights up. Okay, so for your assessment question, it says, how do they work? I'd be great, guys, if you can say what I've just said there, which is obviously putting pressure on the crystal creates a voltage, and that voltage is used to, and then you throw in your own example there, right? Like I said, I gave you 3. I gave you a gas top stove. I gave you the barbecue. Once again, it's lighting the gas, and I gave you the lighter there. All right, sweet. All right, magnetism. So this is an important one. So I will have talked about the AC and DC stuff with you guys already. All right. A generator is what is responsible for producing AC. Okay. So I'm just going to draw, or attempt to draw, you know how it is, our AC wave here. Not in that color, I'm not. Okay. I've done well. I'm just going to extend the black line. And that'll do. All right. Get rid of that. Sweet. Okay. So remember, let's just go over the bit of revision to make sure we understand. The top bit is plus. Bottom bit is minus. Well, positive and negative. I thought you said that was AC. It is, okay, because DC doesn't have a negative cycle. It has a negative conductor, which is confusing, the black cable, but it doesn't have a negative cycle. It doesn't have anything here, right? And because what the cycle means, like we covered before, is that at the top, the current through the circuit is traveling in that direction. So it's going to the load. If I draw a circuit underneath, circuit. I'm going to draw the resistor as a rectangle. All right, lazy, I know. There's nothing wrong with using rectangles as symbols for resistors. That'll do. We'll finish off this circuit here by adding in a positive conductor. So I've made a silly mistake here by calling it positive because this is AC. Even the best make mistakes. All right, so what I'm going to do, I'm going to do a, what color should I do it? I'll do it white. I'll do a white circle to give me a bit of room. Then I will do another circle in black, like that. Beautiful. Look at that. And then we'll just do our little AC symbol. We'll do our AC symbol in there. All right. There's an AC circuit. Okay. So why have I drawn that? Because let's look at how the top one relates to the bottom one. So we'll do our arrow to show that they relate to each other. All right. So this part of the cycle here, all right, how is that made? All right, so it's made, once again, I'm going to do my magnet. North, south. Okay, there's my magnet in that position. All right, here, this is a very simple way of explaining it. All right, this, if you actually get a generator working, this is how it works, but it doesn't look quite as easy as this. All right, that's my conductor. Okay, so in my conductor, remember, I have some very big and strange sized electrons. Okay. Now remember, it's the electrons are the ones that move. Minus, minus. Right, that's supposed to be all the same size and shape and all on, but art was never my forte. All right, so in this position here, these are neither experiencing anything from the north or the positive. I'll just put that at the top, all right, to help us out. And we'll say that's the negative, south, negative. Okay. All right, so they're not experiencing any push or pull from any of these. So where are we at this point here. We're at the start, all right? We're at the point which is there. We're at nothing because no current is flowing at that point. No current is flowing, so these are not moving at all. All right. So the positive cycle, okay? What happens in the positive cycle? So what happens in the positive cycle is this is going to start to turn in this direction. Like that, all right? And what we're going to get eventually, it's kind of hard for me to do, all right? So we're going to have a few stages of, impossible for me to do, all right? So let's just do it halfway. We're going to have it there, and then we're going to have it there again. Okay, stick with me. So we'll just do my, right, so my north is there now. South is all the way over there. And then we're upside down from where we started. So can you see that this magnet is spinning, all right? It's spinning, okay. So there's no force initially. So we start there on the graph, all right? And then again, at the bottom, nothing is flowing. So technically this is off, all right? Okay, so as this starts to turn this way, we need to think about what happens when a plus meets minus. Okay, what does it do? It attracts. Okay, so when it moves, it's going to start to pull them towards it. It's going to start to attract these electrons, all right? So in this one, once again, my electrons are in here. All right, and these electrons have now moved all the way towards, they're moving all the way and they're attracted because of the force between these 2 points, all right? So the north or the positive side of the magnet is attracting these and it's pulled them towards it. All right, where are we now on the graph? We are, because it's at its most strongest point, it's flat, it's facing, all right? We're going to be right at the top now. We're going to be right at the peak. The peak point there is where that magnet is, all right? And then from here, the magnet obviously is spinning much quicker than what I'm doing this. It's continuing to spin that way till eventually it gets to the 180 degrees. Obviously it's spinning in a circle, so it's going to spin 360 from start to finish. All right, so we've gone to 90 degrees and it's moved that way and it's continued to go. But as it's moving away from the electrons, its force now is decreasing. So notice it's still moving in the same direction, but it's now getting weaker and weaker and weaker. All right, until we get to this point. And then this point at the bottom, again, we've got our electrons. But you guys should know now the story, okay? What else is going to happen here? Okay, so once again, I got my electrons. But what's happening now? Which way are they moving? They ain't moving anywhere, all right? Because the magnet has done its 180 degrees and now we're back to zero, all right? One thing I forgot to mention, apologies, is that in this point there, in this cycle here, the current is going through the circuit in the positive way. So it's going that way. That's the positive cycle, all right? It's going from positive to negative. So it's going that way. Obviously, for the other cycle to exist and for it to get back to the start, it's got to travel the other way. All right. So going back to at the bottom, at the moment, nothing is moving anywhere. Okay. So I'm just going to erase this one. Because this is where we started. So this is going to be the end. So can we move from here now? I'm going to alter this one for it to be the other way around. Okay. All right. So this one is going to now turn, and it's going to turn this way, and eventually it's going to move its way down. So this one is going to now turn into this drawing here. All right. And this drawing here is going to have it south there. So this now has traveled 270 degrees. So now it's the opposite of what we had earlier. So now we have a very strong repelling force between the south end of the magnet, which is our negative end, and our negative electrons. Remember, once again, it's the electrons that move. So now, if they're going to push, south is going to push these away, they're going to travel that way now, this time, okay? Which is the other direction that they were traveling in earlier. So that means what's happening at this point, or where are we on the top part? We are at the strongest point, you can see there. There's obviously points between there, which are all these bits that I haven't marked. I'm just marking the strongest parts and obviously 0, okay? The strongest part is going to be the peak of the negative cycle, all right? I always was confused when people used to say the negative. I thought, well, what does that mean? It just means it's going the other way, all right? Okay, so that's that bit here, all right? And then this bit is going to continue to rotate. So this one, this magnet here is going to continue to rotate in this direction until it finally becomes there. And this is where we started. And if we come back to, so I'll tell you what I didn't do again, I forgot. Show on the drawing. So this second step here is when the current was going in that direction. All right. You guys should probably have known that, but I'll write it in anyway. I don't want to take or assume anything. All right, so that was the current going in the other direction in the bottom loop. All right, and now it's got back to its original starting position. So I can delete these. I can delete that. And really, I can delete these bits just to leave me with a nice clear screen of what I'm working with. I've now where I started. So where am I on my graph? I'm right there, which is where I started. And if I was to draw, which I'll just do so you can see what I'm going on about, gets back to here and then it starts the cycle again without the bump. And that's how the generator works. That's a single wave coming off the generator. All right. If you guys are in, so that's single phase. All right. Single phase means one live or one phase or whatever we call it. All right. One live cable. That's one cycle of it. All right. Now, I'm going to explain later on in the course three phase. Three phase is just another other places where we've got cables coming off. So it's pushing cables there, then it gets to this one that we just talked about, then there. So basically what you've got with three phase is you've got, it's very impossible to draw with a mouse, you've got three different starting points and they all follow the same. Right. I'm not going to go into that, 100% not. Not now anyway. All right, so hopefully that's quite a detailed explanation of how the generator works. But it's really, I'm hoping it's really straightforward now. Obviously the north attracts because it's positive. So it's going to attract the electrons this way. As it's turning to south, it's going to push them that way. And that, like the tide going in and out, is how our AC works. All right. Beautiful. Big subject, guys, at this stage of the course. Hopefully that's pretty clear. If it's not, get in touch with us, and we'll see what we can do to help you. Obviously, the student portal has those videos as well. All right, the engineering mindset is really good at explaining this kind of stuff too. All right, moving on. So my drawing was far better than this, obviously, but you've got a slightly different type of generator. This one has a stationary magnet with a coil of wire spinning. The reason I drew what I did is because I think it's much easier to understand the way I explain it than looking at this. As this spins, you're going to see this light flickering on and off. The faster it spins, the faster it's going to flicker, and eventually, in this country, 50 hertz means that this is going to spin 50 times a second. This thing's going to be flickering on and off so fast, you're not going to see it. But what you will see is the ammeter going positive to negative. Once again, positive and negative sounds complicated. It just means that the current is going that way, then that way, that way, then that way. All right? Should be nice and easy. All right, I'm just going to have a quick drink, 2 seconds. All right, what do we use to turn a generator? How many examples can you think of? So there's only a quick few picture examples. You've got some petrol powered generator here. All right, so you've got a petrol motor that will spin, and then the motor shaft will be connected to the generator. All right, that's one way of doing it. Other generator examples here, you've got the inside of the guts of a wind turbine. As the wind turns the blades are connected to the gears and stuff inside. They are responsible for turning the generator. And the generator, like I just said, is basically turning the magnet and breaking the field, which is how it works. All right. There's another example, but that would be obviously the water flow is turning that, and that's how it works there. Okay. All right. Just to go back. All right. I understand that you guys have got assessment questions to answer. All right. One thing I want you to do is understand what I'm saying. But it's also really hard to put it in your own words. Okay. So with the mechanical one, all right. What we were going to say is that when a coil turns in a mag, when a coil turns in a magnetic field, it induces a voltage into the coil, which is then used to power our circuit. So, excuse me. All right, so it's a very basic little explanation there to help you with your assessment, right, guys? I don't expect to see that exact writing in the assessment. You guys can have a little Google about how a generator works. All right, I've given you an explanation there. You can talk about turning the magnet. All right, I was pretty much talking about how the generator turns the magnet, and then obviously the current is going to move through the circuit. I know the assessment is talking about how it creates voltage. When the coil, it's hard for me to draw on something like this. Even when a cable goes through a magnetic field, so just very, very, very quickly, all right? If I've got a north magnet and a south magnet there, capital N and then S. Okay. What we're saying is that if I had a coil of cable like this, I'm just drawing it all in red, it doesn't matter, okay? If I had a loop of cable like that, and then I spin it, then basically the coil will do the same thing as what we talked about earlier. That cable, which I had the electrons going back and forth, That's exactly the same thing, all right? So what happens is, I'll add it in here. The coil breaks the lines of flux in the magnetic field, which creates the voltage. Right, so combination of those two, how it works, right? So if I was to draw that, I'm not. So you'd have a weaker field there, and a much stronger one in the middle. These lines, these make-believe lines, you may have done it as an experiment when you were younger. Two magnets, together. Throw iron filings, and they will copy the lines of flux or copy the strong lines of magnetic field. Okay, these imaginary lines that you can't see, if you break them with a cable, then you get a voltage out of the cable. All right, it creates a potential difference. You get a voltage. What type of voltage? Because it's going from north to south, it's going from positive to negative, you're going to get a voltage AC out the other end, which is what our generators do. Okay, all right. That takes us on to thermocouples. All right, so what is a thermocouple? Thermocouple, as you can see there, is a temperature measuring device. All right. This is the kind of one you'll see in cooking and stuff like that. This is the kind of one that I used to work with in the steelworks, measuring big temperatures and things like blast furnaces. All right. The difference between this one and this one is what we call the type, and that would be the two types of metal that are inside. All right. The types of metal inside, and I'll go on to the next screen to explain how it works. So you've got, and this will help you for your assessment, is my explanation at the top. So you'll have two dissimilar metals, two dissimilar metals together. All right, what those two metals are will dictate what suitability the thermocouple has to measure temperature. So we used to use type K, which goes up in the thousands of degrees. The one which you saw earlier for measuring chicken and food will be much, much less than that. All right. So two dissimilar metals, when exposed to heat, create a voltage between them. All right, and that hot end is over here. It's called the hot junction. Hot end, hot junction. As you can see there, it says junction. All right. So this is the heat. This is what we're measuring. All right. So let's say it's the food. This is the food over here because it's hot. We've heated it up. All right. So we poke it in, and then the heat creates a voltage at this end. Okay. Two dissimilar metals, when exposed to heat, create a voltage between them at the hot junction. This voltage is converted to a sorry about me talking and typing. Temperature reading at the all right, so this voltage is converted to a temperature reading at the measuring device at the cold junction. So like there, you've got a thermometer or a temperature reading or something like that. Okay, so how does it do that? So basically, that will help you with your assessment, guys. So over here, we'll have something like, let's say these cables are designed to have a 0 to 10 volt reading. Okay, well then that over here will be 0 to 10 volts. And there'll be something inside the cold junction which will be clever. And you'll say, well, 0 relates to 0 degrees. 10 volts relates to maybe, I don't know, 100. 100 degrees Celsius. So that's the way they work inside, all right? So for example, if this hot end now was measuring 5 volts, what would we see the other side? So 5 volts would be halfway between there, which means we'd be halfway between there. So this would be showing 50 degrees. That's as easy as that is, okay? That's how it works. 2 different metals. So some clever dude discovered that when you put 2 different metals next to something hot, creates a voltage. And then they've worked out a way to change that into a degrees reading, and that's how they work at the end. All right, beautiful. We're not going to go into that too much. All right, I've told you how they work. Once again, you can research that further if you're interested. All right, clear all. If I'm going a bit too quick at this point, guys, obviously just go back or pause the video. All right. Okay. So where do we use light to electrical? All right, so light being photons. All right, photons are particles of light. Where do we use that? All right, so hopefully give you enough time to think. Hopefully all of us thought of, I said photons, and you don't call them solar panels anymore. If you're in my course, you call them photovoltaic cells. That's what they're called. All right, solar power. When you guys are learning about renewable energy, solar means heat, all right? Solar heat, and we've got solar thermal is one, and we've got solar photovoltaic, all right? Photovoltaic means that photons produce voltage, all right? So how do they do that? All right, here we go with Art Class 101. This is going to be impressive. So here is the sun. All right, and the sun sends down photons that crash into the panel. All right, and the panel is made up of a very clever material, and that material is made up of electrons. All right, so like it shows here down the bottom, the photons smash into the panel, and here's my photon smashing into the panel there. And electrons these days are black, apparently. And what it does is it knocks an electron out of the panel and takes its place. And that electron then makes its way through the circuit. All right. And then one of the electrons who was just minding his own business at this point. Why is that not working? One of the electrons that was just sat there now takes the place of the gap that's just been created by the photon. All right? And as you can see, as the lights smash into it, it creates all these millions and billions of electrons will then travel out of the panel through the cable out into the circuit. All right. And when I say out into the circuit, the ones that are here then come back in to replace the ones that have been knocked out, and that process continues. All right. So you've got that kind of setup going there. How many directions is current travel in? Well, it's leaving this way and it's coming back in this way. That is, they are both facing in the same direction. So solar panels produce DC, direct current. Okay, they're one of the few things that produce DC. All right. So how do we use them for our houses? All right, well, not that you can see one on the house on the left-hand side, but what happens is that the DC comes down and it either goes to a battery bank to charge the batteries, or it goes into a little box on the side of the house, which now we can see there, and that is called the inverter. And an inverter is a very clever thing which turns your DC production and not to go into too much detail or any detail, but it converts my DC out of the panels into an AC for me to be able to use for my AC loads in the house. All right, so it changes it from there, from DC to AC. That's what an inverter does. Let's write the word inverter in there. All right. So the inverter is what does that. Okay, converts DC to AC. All right. So how does it work? So let's, for your assessment. All right, I'll clear my drawings here. All right. I'll move on to the next page. I'll do a write-up for you to help you with your assessment. Okay. So photo. By the sun's photons knocking All right, there's your write-up for what they are, how they work, okay? Okay, like I said, guys, right, this is a recording, so I'm not going to wait. I'm going to clear that. You guys can go back and pause it to help write that in. We need to move on. Okay, so got two things left to cover, transformers and batteries, all right? So what are transformers and batteries? A transformer is a component that converts voltage from one level to another. All right, you can get technical about these, but we're not going to go into them in that much detail. All right, so transformers, component that converts voltage from one level to another. All right, I'll show you on the next page basically what they are, how they work. All right. Okay. So what do we have? So we have our primary winding on one side, and we have a secondary winding on the other side. Okay, so these are two separate transformers, right? So don't take both of them into account. We're just looking at one of them for now. All right, so primary, secondary. So the primary is connected to the supply, and then this would be the load side. Okay, so this is an iron core, laminated iron core, and then you've got these coils wrapped around, all right, from your supply. Okay, so this is how they work. The number of coils is the important thing to take into account here. Okay, if a tran has more coils on the primary compared to the it is a step, what do we say, more on the primary compared, so it's a step down. That means a step down transformer, okay? So that means the voltage out is less than the voltage in. Okay, so what do I mean by that? So if this one here was step down, which it is, this could be used for example, a pool light. Okay, so if I'm looking at that, that could be 230 volts AC. They only work on AC. I'll talk about why in a second. That could be 230 volts AC in. That could be 12 volts AC out. All right. Notice that there's more coils this side to there. And what they do, and this is going to be quite a good way of showing you this, is with a coil and a current flowing through it, you get a magnetic field. Okay. So this magnetic field is going to be doing this. It's going to be going up and down. So we just looked at the sine wave going up and down as the magnet is spinning. This here is a sine wave, all right, the thing we just talked about. So with that happening, the magnetic field is going to go like this, all right. So notice that when it goes like this and it gets big, that's called expanding. Notice that it's expanding over the secondary winding. When it expands over the secondary winding induces, or the voltage jumps across into this one. So this one is doing this because it's a big one. And then if I take that away, this one is now doing that. There's less coil, so it can't create the same size, but it's now creating its own expanding and contracting magnetic field. So this is now working the same way as a generator does. It's now producing an AC out, but it's only got a small field doing it. So it's only got a small voltage out. See that? Small field this side, big field this side. Big field this side because of the lots and lots of turns, okay? If this side had less than this side, so apologies for what this is going to look like, but let's say there was a ton of windings on this side, lots more than the primary. All right, then what I would have to do is delete that. That looks terrible. All right, I am aware of that. All right, so you got 230 in. This time I may have 1000 volts out. Who knows? Okay. It doesn't matter about the value. All that matters is that this time, once again, I've got my field from this side, from my primary. So, but again, it's jumping across into the secondary. But because there's so many turns this side now, this side is massive. Wrong way. This is a massive one. I'll come back and start it over here. So much bigger than the primary side, okay? So that's how it works. Obviously, I can change my sentence at the top to now say, if the transformer has more coils on the secondary and the primary, it is a step up transformer. All right, those are the two main types that you're going to deal with in this course, guys. It's a step up and a step down. One changes the voltage up, makes it higher. The step down makes it lower. All right, you need to be aware of the different types, step up and step down, because when we look at distribution, we're going to be looking at from the power station, we step it up, we send it across the country, and then when we get to your neighborhoods, we then step it down and then step it down again, and then it's safe enough then to bring to your house. All right. Voltage is pressure, remember, and over distance we lose pressure. So a transformer is used to increase the pressure, to send it long distances. Then we reduce the pressure down so we can use it in our houses. All right. So we've got those two explanations there. A few other things which are going to help this assessment and others, all right, is that it works with the two coils working together, which we call mutual induction. Mutual means two things working together. Induction means that the voltage is jumping across, okay? It works with an expanding, contracting magnetic field, which induces voltage into the coils. All right. Now then, just one more note on transformers. All right. Now, once again, guys, right, this is just the basics. If you want to learn more about them, have a look on our webpage. You've got the engineering mindset. He will go into it in more detail than me, but you can also Google these things as well. All right. Another one, and this is an assessment answer, only works on AC. Why does it only work on AC? Because of that sentence above what I've just written. Expanding and contracting. Now, DC doesn't have a contracting. When you switch on DC, it will expand, but it doesn't contract and expand, the contract and expand like I did earlier. All right, DC would basically do this and just sit there. All right, so it can't possibly jump across. Whereas AC is it jump up and down, up and down, up and down, up and down. That expanding and contracting and expanding and contracting is the magnetic field moving across the other coil, and that's how it jumps across. Okay, DC will just do this, and it doesn't matter even if it is over the other coil, because the other coil doesn't notice. It only notices when there's movement. Okay. All right, that's quite technical there, guys. I know the session is going on quite a lot, but I'm covering a ton of stuff. Hopefully you're learning a load of stuff, okay? All right. I'm going to click onto the next page. Now, this PowerPoint is available on the website, okay? So if you guys want to read this stuff, I'll fly through it. I've just written these things down, and this is the explanation. Hopefully I was close to it. All right, transformers operate on the principle of mutual inductance. Induction, inductance, same thing. When one coil induces voltage into another coil, all right? Reading that means nothing without seeing, hopefully, the illustrations and stuff I did for you, okay? When the primary winding of a transformer is connected to an AC supply, the current flowing through the winding produces an alternate magnetic flux in the core. Right, that is too complicated. Hopefully, my explanation was a bit simpler, hopefully. Notice that it expands and collapses, and then once again we've got the words jumps across into the secondary winding, and then the size of the secondary winding, secondary coil, it governs this next slide here. Okay, if the primary winding has more turns than the secondary, the voltage in the secondary will be less than the primary. Step down, and then the opposite is true for the step up. So you've got your two main types of transformer there. All right. Chemical to electrical. So the last one we need to talk about, and we have talked about it already, is the battery. All right. So the battery, you're going to need an explanation for it. So battery to this. Where have we seen that before? We saw that in our two dissimilar metals. That was in the thermocouple. Well, this time, two dissimilar metals again, but this is in an electrolyte solution. All right. An electrolyte solution, guys, is something which has ions. All right. And ions is something which will allow current to flow. Okay. All right, so when the two different metals in the a potent I'll use the word made or developed or created, that's better, is created, which enables the battery to push through circuit. All right. So an electrolyte is like an acid or an alkali or something like that. Okay. All right. An easy one to think of for your own little experiment is if I have that, which is not that. If I have a yellow one, if I have a lemon, all right, and if you put a piece of copper in your lemon, and you put a piece of, I don't have gray, so we'll do that. Put a bit of steel in there, galvanized steel or zinc or something like that. Two different metals in an acid, all right, you will get, not the very big one, but you will get a voltage between the two. Okay, it's the same principle as a battery. You've got you guys have all heard of the term battery acid. All right, so it's acid, it's an electrolyte. Okay, two different metals, put them in there, and then a voltage is created between the two. Connect something to the voltage, and it has the potential for current to flow. All right. Okay, let's get rid of that. Taking us on to one of the last slides. What is the most common form? Obviously, I just went through the battery. Okay. There's a write-up on the battery that you can also use, okay? It mentions the lemma at the bottom, all right? A battery cell consists of two dissimilar metals, positive and negative electrodes in an electrolyte, okay, which is the acid. You can produce a very small voltage using lemons, copper, and zinc galvanized nails, and then tells you about that at the bottom, all right? One of the things I need to talk about for your assessment underneath the battery explanation is connecting batteries, okay? Connecting them in different ways. All right, so there's two different examples of batteries there. Now we can connect them in series and parallel. Okay, batteries connected in series. All right. So if I was going to connect these two in series, I'll show you how I would do that in a second. All right, so you would add the voltage. But the amp hours, which is how long a battery lasts. For example, if I look at a Milwaukee drill, it'll be 18 volts, 5 amp hours. All right, so the volts is the power it can give. The amp hours is how long it can last. All right, so amp hour stays the same in series. Okay, so if I wanted to connect these in series, I won't do it in color, but I would do from there into there, out to there, into there, out to there, and all the way back. All right, there's a series circuit. There's one path for current to flow. So here's my current comes along, and there he goes. He goes through there, through there. All right. This isn't exactly what happens, but there's a series. All right, so out of that, if that's 12 volts, that's 9 volts, then you add them together and there's your total voltage, okay? But the amp hour stays the same. Okay. Batteries connected in parallel. Total opposite. Voltage stays the same. This time your amp hours add up. Okay. So a 18 volt 2 amp hour battery, if I was to put 2 in series, would give me 36 volts, doubling the pressure, so it isn't going to last as long. 36 was still 2 amp hours. All right, annoying. Okay, if I put the same 18 volt battery, 2 amp hour, you guys already know what the answer is going to be here, 2 in parallel, that would give me 18 volts. Well, I've doubled my capacity now, double the length of time it's going to last. So it's going to give me 4 amp hours. All right. So that means if I want to get more voltage out of my batteries and more current, I'm going to have to use a series and parallel combination, all right, to get that. Okay. Just to finish off this one, guys, if I was to connect these batteries, get my cable covered, right? Then I go to my nugget. I go to my positive side. Sorry, technical issues. So I go to my positives, and then I would go to my negatives. So over there. All right. So like we say with any parallel, is each one has a black, each one has a red. Whereas before, really, if I drew it in color, it would have been the red cable going from there to there, and then back from the end. Beautifully drawn. Clear all drawings. Okay, so that takes us on to the final slide. Okay. What voltage is produced by a single AA battery? That's 1.5 volts. What voltage is produced by car battery? They are 12 volts. Both of them DC, remember. What voltage comes out of our domestic war power points? That is 230 volts AC. What voltage is used in industry? That's 3-phase. Well, it's too early days to go into that, but the answer you're going to see there is 400 volts. Okay, we'll be going into that in later sessions. All right, at this point we've covered a load of stuff already, and that's going to take too long. All right, just to finish the PowerPoint off, guys, this is the last slide. This just confirms what I just talked about. So to increase the voltage using batteries, connect them in series, connect the amp hours, connect them in parallel. To decrease both, they need to be connected in a series parallel combination circuit. All right. Okay, session reflection. When we're done. Explain what voltage is using an example. We should be able to say that it's the pressure, all right, that pushes through the circuit. Your example could be water pressure, air pressure, or electrical pressure, whatever. Potential difference, the difference in electrons from one place to the other, measured in volts. Understand how to measure voltage. We measure it by comparing from the red to the black, from one side to the other, the difference from one side to the other. One meter is used, that is a voltmeter, and a unit is measured in, which is volts. We've also covered today the dangers, all right, of connecting it incorrectly, which we covered in the start of the session. All right, identify and understand the different ways voltage can be produced. All right, we covered the generator, the thermocouple, the photovoltaic solar cell. We've covered the piezo-electric crystal. We even covered friction. All right, and we also talked about transformers that could change voltage from one level to another. We do have a session later on in the course which talks about distribution. All right, to talk about distribution, which is sending voltage all across the country, up and down, and so on, we need to know what creates the high voltage and what changes it from high to low, which was the transformer. All right, so we'll be, as long as you know what they are and they change voltage from one level to another, then that enables us to teach you about the distribution later on in the course. All right. Typical voltage from a range of environments. We talked about 1.5 volt AA, and that was in the last few slides we covered there. 12 volt DC car battery, 230 volt in your home single phase, and 400 volt industrial 3-phase. How to increase voltage and amperes using different circuits. So talking about batteries, increase voltage by connecting them in series, increase amp hours by connecting them in parallel. If you want to increase both, do it in series parallel. That again, series parallel, series, start again. Series on its own is covered later on. Parallel on its own is covered later on in the course. And then series parallel is covered later on in the course. All right, so you have much more of an idea of what I'm talking about when we get to that point. Otherwise, guys, that's me done for this session. All right, thank you so much for listening to that. If you didn't listen to it in one, I understand, but that gives you everything you need there to complete the assessment up to the question which says, what are the 4 factors that affect resistance? All right, that one hasn't been covered in this session. That is going to be what we're going to be talking about in our next session. All right, thanks for listening, guys. Any questions, obviously get in touch.